So good afternoon, everybody. We welcome today Thomas Hancock. Thomas is a research fellow at the Choice Modelling Centre and Institute for Transport Studies at the University of Leeds. His main research interests are understanding the decision-making process, the integration of choice modelling and mathematical psychology, model specification and interpretation, and moral choice behaviour. His work thus far has focused on the implementation of decision field theory and ideas drawn from quantum cognition within choice modelling. Today, his presentation is on quantum choice models, a flexible approach for understanding moral and normative decision-making. So over to you, Thomas.
Great, thank you very much for the introduction, Bev. Quantum choice models are a relatively new concept. I'll go into a bit more of the background shortly, but basically the idea here is that we had a call from a colleague at a conference who wanted to better look at how we look at and understand moral decision-making. So we thought that this newly developed model that we'd come up with based on quantum choice models would be a good approach for us for this, and we've kind of gone from there. So first, I'm going to take a step back and think about kind of what actually is choice modeling, what do standard choice models look like, and that'll bring us onto quantum choice models. I'll talk about the example applications that we've done so far, and then I'm going to talk about how this fits in with robotics and autonomous systems, normative choices. What would this actually mean? What does this all mean for if we've got robots making decisions? So let's start with a brief introduction to choice modeling. So there's a number of different ways of studying decision making, and these are all quite surprisingly separate. So, for example, mathematical psychologists would look at understanding the decision making process. So they're really wanting to know what is happening in the brain. How does the brain make decisions? Choice modeling itself is more about predicting and forecasting choice behavior. So it's kind of looking at demand for products. It's looking for understanding why we choose the things that we do or make the decisions that we want. And it's really focused on optimizing that probability of understanding a given choice. Then there's decision optimization, which is based in decisions research, where people might look at how do we actually optimize a decision? How do we help someone make a decision? So that might be particularly relevant, for example, in the context of sort of surgical decision making, for example, where there might be a clear best outcome, but maybe it's not most likely in terms of probability or something. So yeah, there's going to be different factors at play, and that's aim there is to aid decision making. Whereas I come from choice modeling, where it's kind of understanding decision making. And finally, understanding how the brain actually encodes, evaluates, or chooses options. So a sort of neurobiology approach. Now, all of these could be important in the context of autonomous systems, but choice modeling and decisions research are probably most likely to be useful, I think, for informing how we might automate decisions. So now I'm going to talk a little bit more detail about the difference between choice modeling and mathematical psychology. And this is where most of my research comes in so far. So choice modelers, can we explain choices, sort of outputs, as a function of the inputs? So models will be designed such that we can easily trade-offs, so you can get relative importance measures. So for example, how important is travel time in comparison to the perceived safety of a different route? The quality of an alternative, that's usually called a utility, is normally not affected by attributes of other alternatives. That's just the mathematical setup. It's designed to be simple. The utility or quality of an alternative is normally considered to be constant. So usually when we're not looking at a dynamic process, we're looking at a sort of snapshot. Mathematical psychologists slightly different. They want to know how the brain works. They're going to look more at the decision-making process. That might involve looking at eye tracking. It might look at brain scanning, for example, EEG. So they're really looking at how is this person looking at this data and looking at these alternatives and making their choices. So much more importance given to that decision-making process. And models must explain these context effects or they're deemed insufficient. So basically, there's a number of effects that have been found within behavioral economics, and mathematical psychologists try to understand how those effects occur. So they try to build models that explain those various effects. This makes these models often a little bit more complex, and they're often based on simulation, which makes it harder to use these in real world data or real world choice contexts. And they do often have this sort of dynamic utility. So the preference for different alternatives will change over time, and that's explicitly captured in the model. So for example, it might be that you have a certain preference for choosing to drive to work. You look out the window and realize it's a lovely sunny day, and you think, actually, I want to walk or cycle today. So there's that recognition that there's this, so a lot of choices are dynamic in nature. So really what my work thus far is focused on is trying to unpick these two different approaches and see how we can differentiate them and see which contexts they're best suited for. And our current idea really here is that better understand the decision-making process, then you're going to have more inputs into your model. And that means that the mathematical psychology model may be better than the sort of standard choice model. And this is where the quantum choice model. So what sort of real-world problems might we actually be looking at? So here's a very nice scenic route on the coast of a recent holiday I went on. But this was not a safe road. It did not feel safe in the slightest. I don't know what would have done. It would come up against someone driving the other direction. So how much would you be willing to pay to make this road safer? So, the local tourists might have to try and think of, how much would we be willing to spend to actually make this road safer? Or, how often do interactions actually occur in this? Is it actually worth it? So something that's quite hard to put a price on, basically, is the sort of thing we might look at. Some of you may recognize this picture, those of you based in York. This is just looking from the Scarborough Bridge in the centre of town, over the railway and over the railway bridge that goes over the river, and this is looking up. And this is, I did used to commute this way when I went into Leeds, because I actually live on this side of York. I'd walk down this river path and then into the station. So how much might you be willing to spend to protect from flooding? So for example, people who live in these houses on the right, they are going to spend a lot more because they're really invested in making sure their houses don't get flooded. Whereas the average York resident may not be willing to, increase their council tax to pay extra for flood defences quite as much as these people. Congestion is another big one we look at. So, for example, how might we reduce congestion? How might we implement what sort of options can we come up with that would help facilitate reducing congestion? So, for example, my supervisor for my PhD looked at a project in terms of understanding how to implement one of the new Sydney harbour tunnels. So they were looking at how to best maximize its usefulness. So what do choice models actually do? We build mathematical representations of the decision-making process, and this model will generate probabilities that a decision maker would alternatives. These models are based on econometric and psychological theory to explain decision-making behavior. So once we've got these models, what do we actually do? Well, we really, one of our main aims is to put prices on things that do not explicitly have. So we're estimating what we call willingness to pay, sort of value for certain goods. So for example, for travel time or for green spaces or for safety. So for example, when the government was looking at building the HS2, they would have conducted a survey where they tried to understand how much are people actually willing to spend to save that bonus half hour that we get, reducing their time from Birmingham to London. I don't know if people in Leeds were actually consulted. It didn't seem like it. So we try to rely on choice data rather than the less reliable contingent valuation. So what contingent valuation is actually directly asking people what their willingness to pay is. So that would be going to the average York resident and saying, your council tax is how much would you be willing to add to your council tax to build flood defences? So if you put it up front like that, then it's quite hard to get an accurate representation there, because and it's going to be a lot more biased. Whereas if you use choice data, you can present different alternatives, and then people will have to make trade-offs, and that's more likely to get to a sort of more consistent, more reliable value. So we use these different responses, choice responses, to understand future scenarios. So what might the uptake be for some new vaccine, for example, would be an interesting health case study. So what do these stated preference choice tasks actually look like? So typically what we're doing a choice modeling survey is we're going to ask people a number of stated preference tasks, and they will make some number of choices, and then we will infer preferences based on those choices. So here, for example, this is a study some colleagues of mine did in Sweden, where people were asked, do you prefer this current travel time and your current salary, or to travel 10 minutes further for an extra increase in income? And they were asked a number of different questions of this variety where these numbers were varied. So it might be that for certain values people accept and certain values people do not accept, or they might just not actually care, say indifference. In this case, that was an alternative. So really, what does this information actually tell us? It's telling us, is 10 minutes more commute time per journey worth 1,000 krona per month? Multiple respondents' choices here will give us an observed probability of this new alternative being accepted. And a respondent may value these equally, must be indifferent, but we can change the different attribute values. So we might have 5 minutes for 1,000 krona, we might have 20 minutes for 200 krona, and we'll observe heterogeneity in preferences here. Some people might accept all three of the changes, some people might reject all three. And really what we're aiming to do is try and understand those differences in preferences. So this is where the sort of psychological element of our work comes in. We're trying to understand what drives people to make different choices here. So what will our model tell us? Well, our model will estimate utilities for each alternative, and this happens through defining a relative importance for the different within the data. So there'll be a relative importance for the income, the travel time, and the model will maximize the probability of observing this full set of choices. So you might have 100 different participants, each making 10 choices, 1,000 different choices in total. And you're going to have some probability of each choice in each choice context. You will estimate a model with the different relative importances of different factors and try and maximize that probability of observing all the choices in the data set. So of course, this is going to be a really, really small number, but we're still trying to make it not quite as small. So if you imagine that an average choice context, you might have a model giving you, say, 60–70% chance of the right outcome, and multiply that by 1,000 times, and it's going to be quite extreme. So what we then do with this model output is we'll compute average equivalences. So what is the average income gain required to offset an increase in travel time? So that's quite useful information, and there's certain practitioners, government agencies, etc., that would find this sort of information very useful. So for example, when building HS2, this would be a very crucial question. Increased model flexibility will allow for different preferences across respondents. So there's different ways of doing this, latent class choice models, or using distribution rather than pointer estimates of importance parameters. Now, there's also revealed preference data. So far, I've only talked about stated preference data, and stated preference data is very useful for understanding sort of new contexts, but it's always going to be subject to hypothetical bias. If we use revealed preference data, then we're not going to have that issue, but there'll be sort of different kinds of benefits and different issues. So for an example, we've got here a London passenger mode choice data set. It's what's called. It's 80,000 real world choices made by travelers regarding whether to walk, cycle, drive, or get public transport. And see the full network of choices in the data set there covers sort of most of the sort of central London. So looking at this sort of data, we can really understand what is actually really driving people's choices at the moment. And the more information we have on that sort of choice, the choice alternatives and the decision makers themselves, the more insights we can get. So for example, in this data set, we could see that there was a clear bias against choosing to cycle in winter. So evidently, people are more prone to, or more likely to cycle in the summer. That's not at all surprising, and we could see that in our model results. excuse me. So the RP data really does avoid hypothetical bias, but it's run the same way. So you'll estimate parameters to get the relative importance of different attributes, cost, time, biases towards particular alternatives. And you're again going to try and maximize this probability of all observed choices. We can then test the implication of policy changes. So for example, what is going to be the change in passenger volume if rail fares increase by 10%? What is the impact of petrol price changes in a city, congestion charges, parking price increases, all these sort of factors. We could also look at what's going to be the change as the population ages, or the impact of increased working from home. All of these things we could then explore using revealed preference data. So a bit about typical choice models for modeling behavior. And so typically we have utility for each alternative. So here we've got utility for the first alternative is going to be beta, which is a vector of estimated parameters, and x1 is a vector of attributes describing alternative one. So for example, the utility of the first alternative could be the value of cost multiplied by the cost for alternative one plus the value of time multiplied by the time of alternative one. And utility is typically represented this way as a sort of sum of evaluations of different attributes. And what this will give us will these various points here where we've got on the x-axis the utility for alternative one, the y-axis utility for alternative two. And quite simply, the model will suggest that the alternative that is chosen is the alternative with the higher utility. So above this line here, an alternative two is chosen, below an alternative one is chosen. But of course, we don't see everything that goes into the decision-making process. So there is what we call unobserved utility for each alternative. And this means that we've got these sort of circles here around these points, which is going to give us a probability of each alternative being chosen from the viewpoint of the researcher. So some of this circle falls above the line and some below. So the unobserved utility is represented by this error, and different assumptions about how we define this error will give us different choice models. So for example, the most sort of standard choice model is based on the extreme value distribution type 1 errors, which gives us what we call the multinomial logic model based on random utility maximization. And this is a model that's been used for about 50 years and is still the sort of main choice of model for most choice modelers. It's just a sort of real go-to in our field. So the main reason for this is that the calculation of a probability given a utility is really very simple. So we end up with this sort of exponential of the utility divided by the sum of the exponentials of all the utilities will give us the probability. So we can calculate probabilities for each alternative given some utility very, very quickly and very easily. And we can do millions of these calculations per second on sort of standard computers. So we can process large choice data sets, that one with sort of 80,000 choices in London very, very quickly, for example. We then maximize the log likelihood of observing all these choices. So what this is basically the probability of all the observed choices for each individual. This is going to be multiplied together, and then we're going to take the log of the sum of these likelihoods. So it ends up being, if you looked at without logs, it would be this ridiculously small number. It could be half to the power of 1,000, for example. That's going to be incredibly small. So we work with logs here just to make that number more manageable and computationally easy to use. So what we're going to then do is maximize this log likelihood subject to some set of parameters. So we're going to put in these parameters and estimate the best values for these that best fit our data. So for example, we've got this choice task I mentioned before, where what we'd have is typically what we call marginal utility parameters for the different attributes for salary and for travel time, alternative specific constants for the different alternatives, alternative 1, 2, and the indifferent, and status quo bias potentially as well. So what we have here really is just different number of parameters that will be estimated, and this will tell us something about how people are on average making a choice. So what we can do then is to add in socio-demographic differences. So these are almost always added additively. So for example, we'd have the utility of this first alternative might depend on some different underlying bias if the decision maker is male. So perhaps males might be more likely to stick to a status quo. I don't know. But yeah, we'll find some underlying biases here. And typically you might include gender, age, income, various other sort of standard demographics, and that will likely impact decision making. Now, choices are these differences are almost always included additively, but psychological changes in choice context are also treated equivalently. So for example, if that first alternative is morally questionable, the standard way of actually including that would be this parameter for morally questionable multiplied by if the alternative is morally questionable. So what I'm saying there is if we've got some way of defining which alternatives are questionable and which aren't, then we could probably just throw in this extra constant, which would be estimated in the model. And it's a bit like an intercept. So basically, if you had a logistic regression for you, what this really is a bit like a logistic regression, but for discrete alternatives. So rather than a continuous outcome for alternative 1, 2, 3, etc. So reasons we might not want to use this sort of standard model and reasons we might want to move away from it is how we kind of came to doing quantum choice models. So there's recently been a shift towards the idea that individuals may think differently, and there's this additional sort of complexity in how we make decisions, and that maybe standard models just too simple to actually represent this. So there's all sorts of attempts that have happened kind of in light of this: attribute non-attendance, regret minimization, use of heuristics, for example. But we thought we'd try something that's a little bit more different by using quantum choice models. So quantum choice models, firstly, what's quantum probability? In the early 1900s, physicists demonstrated that the sequence that measurements were taken in affects the final observed values for physical variables. These were then defined as incompatible, and this led to the development of quantum probability. And of course, ordering effects are a very common phenomenon in choice behavior too. So for example, if I want to go to a certain place, that's going to impact which modes I then use to travel to that place. So my sort of sequence of decisions is they're gonna impact each other. So I might choose to go into the city center and then think, well, it's a nice day, I'm gonna walk. But if I choose to go into Leeds, then I'm not gonna walk to Leeds. So there's gonna be some sort of link between choices there. Now, quantum-like models are gradually being introduced into psychology, and this is in an almost new field called quantum cognition. And these have been designed to aim to control for the impact of order effects. So there's this example I'll just use there: destination mode or mode and destination. Another example might be, do you choose to go to an Indian restaurant, then a vegetarian option, or are you maybe a vegetarian, so you then think Indian restaurants are more likely to have foods that you're going to like. So we can use this to test the impact of nudges. So for example, asking someone how much you care about the environment before they make a choice about which conservation program they would choose. And this new idea of quantum cognition has been very effective within cognitive psychology. So we thought we could try and introduce quantum probability in a choice model. So quantum probability is based on the initial idea of subspaces. So for each choice scenario, we're going to have a subspace. Then we're going to have these vectors for each alternative. So for example, the status quo and a new policy. And this looks like it's just sort of standard geometric space, but this is actually in Hilbert space, which means the numbers have real and imaginary parts. So this is where the sort of quantum stuff comes in. And because these vectors are orthonormal to each other, this means that you can really only choose one or the other. So before I make this choice between new policy and status quo, we have what we call a belief state, and this represents our sort of tendency to make either choice, either decision. But before I'm asked to make that choice, I could kind of go either way. And it's only upon being asked the choice, do you prefer new policy or status quo, that I'll actually think about it and make my mind up. So the idea here is that within a quantum choice model, the uncertainty is actually held in the sort of decision maker rather than the analyst. So remember, in the choice models, there was this unobserved utility. So basically, the modeler doesn't know everything about how the decision maker is making their choice. Therefore, there is this error component that comes in from the fact that the analyst doesn't know everything. Whereas in this case, it's really kind of almost the other way around. We're assuming that the decision maker is actually inherently uncertain, but they make a choice at some point. So we're trying to understand what their initial belief state was to basically work out the probability that they went kind of either way. So when they make that choice, what will happen is their belief state will sort of merge onto the belief state of this other alternative, and that will then impact sort of future choices. So how we generate probabilities out of this is that this state vector has unit length, and because each alternative can be defined as modular square of the amplitude for the alternative appearing in the decision maker's belief state, we end up with probabilities that sum to 1. And this sounds a little bit confusing, but if you imagine Pythagoras' theorem, we know that this side squared plus this side squared will equal this length squared. So it's kind of based on the same idea, really. These different projection lengths here and here are going to sum to 1. So we can generate probabilities here if we know what this belief state is. So what happens when we have some sort of change of perspective or a nudge is that we're going to rotate this belief state around in this system here. So this is just summarizing those differences in the structures. So this main difference here was that the decision makers are certain there's unobserved utility from the analyst perspective. In the quantum model, it instead assumes that a decision maker is inherently uncertain. So quantum choice models here could possibly include the underlying deliberation process. So how do we kind of move through this space? They may specifically allow for interactions between alternatives, which is potentially realistic. They may allow for better understanding of choices we make. And they're not going to have that same simple interpretability of parameters, although some useful model outputs like price elasticities can be derived from them. So this has led to 2 publications we've got. The first one was specifically just looking at the defining quantum choice models, and then the second one was looking at it in sort of more decision-making contexts. So how do we actually define these quantum choice models? So to estimate probabilities, we're going to have some idea or some utility or preference for each alternative. So we're going to need something similar within this quantum framework. So basically, we want some function for mapping attributes of alternatives to obtain this thing we're calling the modular square of amplitudes. So this amplitude here, how are we going to define this? And you can imagine that if we've got 2 alternatives here, if I look at the travel time, alternative 2 is better, therefore my state looks more similar to option 2. I look at the cost, option 1 looks better, so I'm kind of moving upwards, meaning that my state is going to look a bit more like this one, and we kind of end up somewhere in between by considering these different alternatives. So you end up with this state that's kind of in between these 2, therefore it might have a sort of equal probability of choosing these 2 alternatives. So our model that we called the quantum amplitude model has the same parameters from the utility model, so that we can make this sort of direct comparison. Basically, we're going to have the relative importance of these different attributes, and we're going to define this quantum, this amplitudes from different alternatives based on some function of these estimated parameters and the attribute values here. I'm not going to go into the specifics here of how we actually define this function, because it's quite context specific, and it'll be dependent on, there's different ways of doing it. So it's going a bit too much into the detail, which isn't an important bit here. But basically, once we've got this way of defining these amplitudes, what we can then do is understand or come up with ways of how these would be adjusted under certain contexts. So for example, if we have a rotation, quantum rotation. So what we've got here is we have this initial belief state over choosing between a status quo and a new policy. Now, if you look at this new policy from a different angle of saying, is this policy ethically justifiable or not? Well, if it is, then our rotation is going to sort of map us to a new state. So basically, if we choose, say that yes, it is ethically just, then that means our new state will be the same as this ethically answerable state. So this is where we now are. And now that we're here, the chances of choosing new probability are, the new policy are much higher. We're much closer to this new policy. So this this projection length here is much longer now, and this one here is shorter. So basically that probability is decreased and this one's increased. Whereas if we say no, that policy isn't justifiable, then our belief is going to reduce for choosing a new policy. So we're less likely to choose this new policy. And there's different ways of constructing this sort of change in this space. And we need to be careful about how we define this such that this belief state remains of unit length. So basically, once we move to here, it still needs to be of unit length. Otherwise, our probability for the different alternatives is going to sum to possibly not 1, which is not a good thing. So in this case, we used, there's a couple of different things we can use. We could use Pauli matrices or Hamiltonian matrices. And this is where we found it incredibly helpful to actually collaborate with a quantum physicist, and he came up with various sort of ways of us doing this, which were very helpful. So now moving on to empirical applications, a couple of case studies. Just yeah, I'll just go through a couple of quick case studies here. So the first data set we're calling the UK value of time data set, and this is 3,000 individuals completing choice tasks that look very much like this example that I gave here, where we've got 2 different alternatives. One is cheaper, one is faster. So basically, how much are you willing to spend to save time? And that's going to be different for different individuals. Now, there are possibly ordering effects in this simple design. So for example, what I've got here is cost on the left, time on the right. Whereas in these ones, time is on the left, cost is on the right. So certainly what we found in general is that in the Western world of reading left to right, attributes on the left tend to have a slight bias. So they become more important. Similarly, alternatives that are listed first tend to be more important. So here we've got, in these two, we've got the cheaper alternative first, and then these two, we've got the cheaper alternative second. So different individuals in this data set were presented one of these different 4 combinations. So basically what we're going to look here is, can this quantum choice model capture that change of perspective, that sort of an underlying difference between what different individuals were seeing? So our basic model is going to have this sort of function of costs and times to derive the probability of each. Standard shift in preference will just have some estimated parameter to shift those preferences. Context shift through a quantum rotation will have these rotation matrices used. So we could use this order rotation if we moved across here, down here, and this left-right rotation if we move across here. And basically what we found here was that in comparison to the standard multinomial emergent model and another model we developed called decision field theory, the best way to capture that difference between different choice contexts was to use this new quantum rotation. And that model had the best overall model fit as well. So basically, this difference was best captured using the quantum model. Second case study, we're now going towards this is one of the case studies from our moral choice paper, where basically what we had was potentially dodgy new transport policy. We're going to build this new roads. It may result in you having less or more vehicle ownership tax. Travel time might change, but this new roads potentially has more accidents or not. So it might be that it's a safer road or not. So there's these secular attributes, what we call them, is tax and travel time. So they're sort of things that don't really affect anyone else. And then there's these injuries and fatalities where potentially impacting human life. So we call these sacred attributes. The individuals in this data set did 16 different choice tasks. So the 16 different combinations here of less or more of each of these. Our colleagues in the Netherlands who did this study in the first place culled came up with what they call a taboo trade-off if the decision maker can choose to save money or time in favor of causing more injuries or deaths. So, for example, this here is a taboo trade-off. So if someone choosing to make this decision is basically saying they value their own money savings and time savings over the fact that other people might be injured or killed. So they came up with a model which they called the taboo trade-off penalty model for whether people chose this new alternative or not. What we're going to do is use this intermediary step of, is this an ethically justifiable choice or not? Now, we don't know whether people thought that or not. So what we did was we implemented this ethical question, basically, if this taboo trade-off penalty could exist. So basically, if there was a potential to save money or time at the cost of lives, then we implemented this quantum rotation, imagining that people were actually thinking that whether this is ethically justifiable or not. And what we found in this case was that the model was best performing once we included this Hamiltonian rotation, so this particular type of rotation. So basically, it seems that the best way of representing the fact that this was a slightly dodgy choice context was to use our quantum model. Now, what did these log likelihoods actually mean? Because they just look like numbers at the moment. Well, we can actually translate these to the average probability of being chosen. So basically, what is the average probability that the model correctly identifies alternative that was chosen? So in the first case, it's 63%, and in the final case, it's 64%, which might not sound like much, but 1% can be very crucial, particularly in sort of large-scale forecasts of, for example, going back to that example again, HS2, that 1% really can make a big difference there if you're talking about a project that costs millions. And so what we see here is the derivation, but the differences between the observed share of choices and what the model predicts. So basically, in each choice context, the model is going to predict a likelihood of accepting the choice or not. And what we found here was that the quantum model had the least deviation from the observed shares. So basically, it's capturing the sort of right percentage of individuals saying yes or no to a particular alternative more often than not. So I'm just going to talk for the last 5-10 minutes about autonomous systems and normative choices. So basically, how might choice modeling help machines make choices? So there's going to be many different situations in which autonomous systems will have to make choices. And in a lot of cases, it might be that there's very clear solutions if the quality of different alternatives can be easily established. So for example, if you're using your sat-nav, your vehicle is going to choose which way to go based on which way is quickest. And for example, you could program an automated vehicle just to simply choose the fastest route. But in some cases, with the moral component, this course of action may become unclear. So for example, is a 15-minute trip on a more dangerous road better than a 20-minute trip on a safer road? And that's going to be dependent on subjective opinion. So actually, that was a very good recent publication that started looking at this sort of ideas. Formal verification of ethical choices in autonomous systems is really good starting point, I believe, on understanding decision-making processes for autonomous systems. But then there's several more questions we can ask. And I was looking at this paper thinking, what more do we need to do? And there's a lot more questions really that we can think about. So for example, how do we actually define or calculate which alternative is best? How subjective or objective is the outcome? How certain are we about the relationship between actions and outcomes? So for example, it might be that there's a very clear result of making a choice, or it might be that there's not. So for example, if I was driving to Leeds, it might look like it's going to be 40 minutes, but there might be traffic or there might not be. So there's going to be some uncertainty even in very simple decisions. Will different users have different preferences? So that's going to be quite a big one in terms of, well, a lot of different case studies. There's a lot of different cases where there's going to be different individuals have different preferences, and how do you actually take account of that? And how important is it to take account of that? And related to that, who should make the choice? Are some people's opinions worth more than others? Should we be looking at road safety experts' opinions on, which roads we build? Should we be looking at the opinions of doctors as to what type of care is automated? And how might attributes the quality of possible alternatives vary is also a big one. So if there's a large variation, then it's a more complicated choice context, and that's going to really muddy the waters. So now I'm going to go back, take a step back and think about this sort of idea of decisions optimization, which I talked about at the start, versus choice modeling. So in decisions optimization, that's really about, can we define a best alternative? Can we support decision makers to make the best possible outcome? Or can we support a machine to make the best possible outcome? That's another way of framing this. So these often use panels of experts to directly decide the relative importance of different attributes. Now, these panels of experts may also come up with proxies for rating the different attributes of an alternative. And typically, this would be for cases where there's a sort of limited variation in the quality of different alternatives. So it would be where there's more clear-cut differences or more definable alternatives in terms of the different attributes. So for example, if I was choosing which laptop to buy, they have very set attributes, different attributes. So processing speeds, cost, width of screen, etc. Whereas some different alternatives might have wider variations or very harder to define attributes. In choice modeling, we're going to look again at explaining choices as a function of inputs. So really, this relative importance of different attributes is estimated, is not sort of stated, and it's based on choice data where there is sort of significant attribute variation in the different choice contexts. So if you can see how people choose in a given context, that will help you understand what the relative importance of these different attributes actually is. And you can do quite clever things in terms of the experimental design of stated preference surveys to look at how to best generate different choice tasks so better understand the relative importance of different attributes. And you will need large variation in attribute levels there. So in a previous meeting with Bev and others at the University of York, we talked a bit about some sort of case studies here. And one of them, we're looking at this case of an autonomous system designed to give insulin. So now there's various different attributes here, the importance of the principle, relative importance of the principle, and the sort of different ethical motive here. So the respecting autonomy or preventing harm. Now, in this case, it's quite a clear case where these attributes you'd expect to have a particular star rating based on expert opinions, and you'd imagine that there's not going to be a huge variation in those levels. So if I asked a set group of people, you wouldn't expect huge differences in what they think these values are. And there's also not sort of multiple different cases here in that if it's you're giving insulin, you're giving insulin. It's not like there's going to be a huge variation there, or sort of different attributes that become more important in different contexts. And this is quite a stable scenario, I guess, is what I'm trying to say here. But cases that will be more suited to choice modeling, which is what we do in Leeds, is when you're looking at trying to understand or model preferences as opposed to a decision. So for example, what do people actually really want in their automated decision making? So for example, if automated car is going to make certain decisions in certain contexts, then you might want to understand the user's preferences. And to understand user preferences, you probably want a large scale data set where you're going to survey more users. And you do need more data for choice models. So you typically have at least 100 decision makers, whereas for decisions optimization, you could probably do it quite easily with an expert panel of 10 individuals or so. Decisions and choices based on these outputs will have value depending on whether average preferences are actually useful. So say I have some large scale data set where I've got all these choices made by individuals. My model will be able to account for some of the variation in preferences, but it will also come up with probabilities that sort of match the sort of average preference. So if you really want to understand specific user groups, then you might need to either target those or really sort of focus in on that group within a sort of more defined context. We also need more attribute variation to actually design different choice contexts for choice modeling. So what do choice models actually give us? And this is going to relate back to a bit about what I've already said, but this will explain a bit more about when and where not they can be useful. So we're going to get relative importance weights for different attributes, which were stated instead in decisions optimization. We can look at differences in preferences quite quickly, and you can do subgroups, sort of users or professionals, for example. We may be able to identify elements of the decision-making process that kind of leads to certain decisions. And we can also quite quickly look at hypothetical data sets or simulated data sets where we look at what happens if we have, say, extreme individuals and how does that impact average preferences. This can also help us look for tipping points in terms of what percentage of individuals have to have a particular style of decision-making for that to become really influential. And we can also look at preference heterogeneity in quite a lot of detail with choice modeling. So how do preferences vary across different groups, and how influential is that going to be in our final model? So a quick final case study. I looked at the moral machine data, which is quite, yes, this is a little bit dodgy, I suppose, but it's quite an interesting case study. So basically, there was this study at MIT where there was a huge data collection effort online, 40 million decisions, absolutely massive number of people went into the study. Basically, because they had a sort of snowball effect where they got people who completed the survey to send it on to their friends. So there was about 1 million different people did this. It was great. So they looked at the classic trolley problem here. So basically, they had various different choice contexts where they're imagining in this automated car is going to crash. Who should you kill? So what should the self-driving car do? Should it save the people on the roads or the people in the car? So there's different attributes in this case. Are there different characters? Old people here, for example, there's a child in the front there, so younger people in this case. And each individual who completed this did sort of 13 or so choice tasks or more. And there's various other attributes here. For example, in some cases it was pedestrian, and sometimes pedestrian or people in the car. Sometimes these people were crossing illegally or not. So you can see that there's a little red hand there, stop. So that's basically these people shouldn't have been crossing the roads. And sometimes they were allowed to cross the roads. So quite interesting case study, I guess. And that's what we sort of looked at here in terms of applying choice models to this data. So the original paper on this used sort of standard regressions. And our regression model has the weakness that all attributes are considered in the same way in the decision-making process. So for example, there's a trade-off between different characters, but also the design artifacts. So for example, you could say from a regression, whether this light is red or green is worth a certain sort of value of life, which is quite a funny sort of odd concept. But basically, you might have a case where 50% of decision makers chose the car, and 50% chose to save the individuals on the roads. And you can say, well, if this light had actually been green, you can sort of work out that probability shift, but you can also work out the probability shift from changing characters as well. So it's kind of saying that the context is almost the same as the characters. Last couple of minutes, we did a quantum choice model on this and found that it did better than the sort of standard multinomial logic model by recognizing that different attributes were of different values. So this is in the quantum space, imagining real parts given to the different attributes or characters, and found, for example, that pets are considered very differently to the other factors. So you can't really trade off a pet with a person, which makes sense. So just a couple of final quick notes. User preferences may not actually be of key importance in this particular. So there's all sorts of things at play here, liability, law implications, not at all considered in the WAD study, not at all considered yet by me in this previous example. So in certain cases, decisions optimization may actually be better. And especially when there's a lot of unknowns, such as the likelihood of crashes actually resulting in death, the likelihood of the crash itself, reliable estimation of the utility of possible alternatives, etc. But we can see here how choice models this is just a quick demonstration of how they can actually be used to understand the preferences of the sort of underlying population. So choice models, in conclusion, are a very useful tool for studying subjective alternatives. So when there's not a clearly definable best alternative, and you want to understand different preferences, then that's going to be really good. Multiple choice contexts are particularly likely to incur varying preferences, is what we found in general. So it's a particularly useful case. Programmers of autonomous systems may likely benefit from the use of choice models to understand preferences, but decisions optimization research is also going to be helpful. So you need to consider which one you actually want to use if you're looking at programming decision-making tools. Finally, we have some evidence to suggest that quantum choice models may better explain choice behavior than standard models. With that, thank you. This is just a very brief advert to the Apollo Choice Modeling software package, which is created by my colleagues, which has been absolutely fundamental to my research. Yeah, thank you for listening.
Thank you very much, Thomas. I've got a quick question for you, and that is, when you have a look at the difference between, do you ever look at real world data versus preference data? Because I think when decisions are made, when you have the benefit of either hindsight or the ability to think things through and to make decisions that are sort of theoretical choices rather than real world data, so the actual decisions that people are made in the moment as the emergency is happening, do you think that there would be a difference in the choice that's selected?
Yeah, so really interesting. Yeah, really interesting question, and it's actually directly tied into a proposal we have currently, where we've got we put in bids for a competition-funded PhD place for a student to basically study exactly that. So we've got an applicant kind of going through the moment who hopefully will be starting October, and what we're going to do with her is that we'll look at using virtual reality to try and make a step towards it feeling more real. So there's obviously hypothetical bias, and the really clear example is that autonomous vehicle crashing case. That's very subjective and very subject to bias. But if you stick someone in a virtual reality environment where they are actually pulling some lever, then it's going to feel quite different. Now, in terms of actually getting towards sort of real observed data, I'd say it's a current thing that we're not really picking up on much in choice modeling. We really should. I've seen a couple of very good case studies on it. One which was actually it's on the Choice Modeling Centre's website, because it was a seminar we hosted a bit over a year ago, maybe a couple of years ago now, where it was looking at stated preferences for vaccine choices and then the actual uptake of vaccines. And that was sort of really kind of closely studied. And I think from memory, they had a sort of 90% matching rate in terms of actually the sort of stated choice and the actual choice. And they were looking at kind of how they could better improve that prediction of whether someone chooses to get vaccinated or not. So there is some work on that, but it's certainly not a big thing yet, and it should be.
Okay, great, thank you. Are there any other questions? Radu, you look like you have a question.
Indeed. So thank you for the talk, Thomas. Very interesting. So I have a couple of short questions. One is, how well do these choice models operate with more than two options? You're selecting examples with two options.
Okay, yes. So they are very, very good for large numbers of alternatives. And actually, that's one of the main things they were designed for. So a very good example of that is a data set we used where we looked at mode and destination choice. And that was in California, and it was across the 52 counties there and 4 different travel modes. So 208 different alternatives. And we're looking at which of those 208 different alternatives were people actually choosing. So that's quite common, is that you'll have sort of hundreds of alternatives. And this is one of the reasons the standard multinomial logic model is very popular, because it can function with hundreds of alternatives. And the main difficulty there lies in actually, can you define the utility for all those different alternatives? And in some cases, that's quite easily possible. So in that case I just talked about, in those 52 locations, we defined what we call attractor variables, which is describing the quality of a place based on number of shops, number of hospitals, number of workplaces, population density, these sort of things. And that would define the utility of the location. And then there's also utility of travel mode as well, car, etc. So then you can build these models up quite quickly. But certainly, yes, if you've got 4, 5, 6 alternatives, that's very normal. And it's just so happened that my examples weren't great, actually.
No, thank you.
Yeah.
All right, so maybe another question I had has to do with the fact that you kind of suggested there is an implicit assumption that I need to select one option, but maybe it is possible to select a mix of choices in the sense of some people stay behind and receive a higher salary and others go first and reach home quicker, right?
Right. So yeah, basically when we do our choice models, our understanding is that there's going to be different percentages of people that choose the different alternatives, even if they face the same choice context. So, for example, you might see that 90% of people say yes to some given alternative and 10% say no. And what your model is going to try and do is come back with a probability of 90% in that context. So basically match that share in the data. But also, if you're thinking about it in terms of being able to choose both, for example, then there's a different set of model altogether called the multiple discrete and continuous choice extreme value model. So what
it's
that
not
does
going to work with flood protection, but may well work with transportation, right?
Right, yeah. So the very common example of this sort of work in our field is looking at time use. So basically, how do people allocate time across their daily activities? So there's this sort of discrete component of the different activities, but there's the continuous component of the number of hours for each activity. And I've got one colleague who's very much leading person in that sort of model. So yes, that is separately studied, but very much possible.
Great. Callum, you have a question?
Hi, yeah, no, that was a really interesting talk. Thank you. So I think you kind of touched upon this slightly implicitly near the end. So I apologize if you kind of talked about this and I'm just kind of reiterating what you went over. So my feeling is because you're using the quantum approach, because you don't understand or you can't fully grasp how the human or the individual got to that decision, to me sounds like that this is just a black box. So maybe this is a bit naive for me to say, but could you just replace the human with, say, for example, a deep learning agent and use your approach to actually better understand the decisions that are being made? So not necessarily like synthesize a controller for it, but actually understand why they're making the decisions that they're making, because obviously, if they're doing something bad that we don't want them to do, then we'd like to actually have some form of explainability, which this to me seems to give some nice understanding of what sequence of events led to this moment. But then furthermore, at least from what I saw from the sort of subspace work in terms of when it will switch to a new policy, to me, that kind of triggers as a nice way of avoiding, say, for example, harmful or dangerous actions or policies. Maybe I'm wrong in this sort of interpretation, or maybe you've kind of already touched upon this, but I was just kind of wondering what your thoughts on that would be.
Yeah, no, it's really interesting. Well, this is something we certainly don't do enough of in choice modeling work, is to actually really in-depth explore the sort of social demographics that kind of go into decision making and how they sort of lead to different decisions. But actually, this touches on sort of part of our current work, which is trying to use physiological sensor data to also better understand decision making. So our idea there is that if we can understand a bit more about how someone's making a decision, then that will help us understand the actual output as well. So it's trying to, if I go back to this diagram right near the start. Here, so what we're saying here is that we'll have some choice context here. We don't know, so this unknown function, how people perceive it and kind of what their input will actually be. We don't know how they process it and what their output is. And what the choice model and mathematical psychology models do is they try and use this and some definable parameters and some function to then come up with probabilities of these outputs. But what we're really saying here is that if we try and understand this process, try and find something in this process this might inform certain parameters of the choice model, which might then better inform our output. So we're kind of trying to open up this black box by looking at what that decision-making process is. And coming back to your other point about sort of sequences of choices, that's also very interesting and something we don't do much of, but that's mainly because to actually really capture sequences of choices can be quite tricky. In certain contexts, you might see something. So for example, that I saw a recent paper that was very good in terms of understanding the inertia behind choosing your commute to work. So looking at, how does your travel your previous day influence your travel the next day? But if it was actually sort of looking at a sequence of decisions that led to sort of morally questionable behavior, for example, then yeah, that's going to be hard data to work out, particularly in terms of what were the different alternatives at this different point, each different point, and how did people go down that track. But we did have a conversation with a criminologist a couple of years ago about this, and I think our conclusion was that it was going to be hard to map those different alternatives in terms of understanding what actually is the choice context. And that's maybe where the pitfall here is, the difficulty lies in kind of to understanding what is that choice context.
Okay. Tim, you have a question?
Yes, thanks very much. Sorry, bear with me for a second. Yeah, it takes me back a little bit to modeling operating costs and the effect of speed on supposed economics of aircraft. But two questions, if I may, and it's a really interesting presentation. When you're looking at a model like the one you've got on screen at the moment, at what point do you sort of split out instinctive reaction from rational reaction? In the context of that MIT example, the last minute braking attempt or decision on which way to steer is more likely to be instinctive than premeditated.
Yeah.
Whereas a decision about which way do I go to work is more likely to be premeditated.
Very interesting. So this is, I saw a presentation, quite a few years ago, that was really trying to look at system 1 versus system 2 decisions, is what they labeled it, is how they labeled it. So yeah, this sort of instinctive or not decisions. And I'm afraid this again goes back to data quality. So can you come up with a choice situation where you can actually say, yes, this person didn't deliberate on this? Now, I think the best way forward in this case would be to use some sort of simulator. So a driving simulator, for example, which we do actually have at the University of Leeds, where you put people in these situations and see how they react, and then really study that sort of brain scanning, EEG data, the physiological data, the heart rates, all of this, to try and really understand, what actually happened to you. And there was a paper by a colleague of mine who looked a little bit at this in terms of understanding, I think it was more the detection of crashes. So when they're going to crash, how soon do people react and actually see it? So there wasn't actually a choice in this, but there was a sort of reaction. So they were looking at understanding how long it took for someone to sort of react to that situation. So that's closely linked. So kind of bring all of that together, and I'd say the way to really study that would be throw people in the situation, see what happens, see how they react in certain contexts, and then look at that underlying data on how the sort of underlying physiological data, and can you unpick the sort of unconscious decision from the rationalized decision. But yeah, really interesting, and it would be great to have the resources to go and do that.
Yes, no, I can understand. Yes, because the F1 guys are starting to record the physiological data on drivers, aren't they, during the races? But the other question was the mathematical one. Part of my reason for logging in today was to try and understand the use of quantum modeling, probability.
Yes.
And bear with me, because I didn't really, it's not a subject I'm that familiar with, but when you introduce the semicircle and the radius of 1, what actually is the basis of the radius of 1, and therefore the ability to apply Pythagoras to splitting the probabilities?
Right, so maybe didn't explain this too well because I went through it quite quickly, but the way this works is that if this belief state is of unit length, then what that means is that if we see here, that means that this amplitude, this is a complex number, multiplied by the complex conjugate, is going to come out at 1 for this here. So the amplitudes of whatever this is in imaginary numbers, multiplied by complex conjugates, will come 1. And if you define this in the right way, then it's guaranteed that these components, so this one here and this one here, when I say squared, it's not really squared, it's the amplitude multiplied by the complex conjugate of those different vectors will then sum to 1. So I can't, it's really hard to actually visualize. And we had a lot of discussions about how you actually represent this. And if I remember when we tried to write up these figures in our paper, we had the description of the figure. We usually try and keep it really neat and short, but we had to have quite a lot of details in there. So yeah, do have a look at our paper, one of our couple of papers, and you'll see there's much more details on the actual underlying probability and how it's actually defined.
So let me ask, sorry.
So I was just going to say we use something called bracket notation on this, which is also explained in the paper. So that would make it a little bit clearer as well, what's actually happening there.
Yeah, so let me just be really a little unfair then and ask the question in a slightly different way. Are you actually saying that's more a construct to help get a model that is usable, or is that actually based on sort of the way quantum probability or quantum mechanics works, and as a model you've taken forward to this situation? Or
well, it's a really good question, and it's something that one of my co-authors sort of hinted at in a recent email. Actually, was saying, what actually is this? It's just some nice mathematics to explain, give you more flexibility in explaining decision making, which you could argue that it is. The people to really sort of ask about this are the psychologists, the quantum cognition guys, who have debated this in quite some detail. There's a paper by Jerome Bussemeyer who really looks at this question in quite some detail, and he's got a series of arguments for why we should use quantum cognition to understand choice behavior. But it's much more detailed than I could go into now. But it's quite a compelling argument, I'd say. So yeah.
No, thanks. Really interesting. Thank you.
Thank you.
Thank you very much, Thomas, and thank you for everybody's questions. It's been very enlightening. But I think we should close now as our time is up.
Yeah.
And if anybody would like to continue any communication with you, I'm sure they can reach you via email, if that's fine with you.
Yes, please. Yeah, please do.
So thank you, everyone, and I'll end it here.
Perfect. Thank you.
Thank you.